Okay, today I will talk about the CHOPS. The CHOPS is a cold heavy air production with sand. The first part is the introduction, issues and definitions. The scope of this report, there are a number of unique operational issues relating to the production of heavy oil and super heavy oil in Canada, and more specifically in Alberta. This report will explore in detail the technical and environmental issues related to cold heavy oil production with sand. It means CHOPS. Also, extensive references to other new process and emerging production technologies will be made. With respect to CHOPS, heavy oil and oil sand in Airbus, some specific questions may arise. What are the similarities and differences in crude qualities and production practice between primary oil sand and conventional heavy oil production? What are the average versus productive capability from an operational perspective? How many wells make up a project for both crews? How are the wells and fields managed and sand disposed? What production technologies are appropriate for various technologies? What is the reservoir impact of CHOPS and is it negative or positive? What is CHOPS and how has it evolved? How many productions comes from other technologies? What technologies complement CHOPS? Are there other emerging technologies? Who is involved in the industry? Name, size of company. What are the producers? Who are the technology developers? Who are the manufacturers? What is the status of the related research and developments? What is the future potential for these crews? Are there many CHOPS fields left to develop? What are the possibilities for enhanced oil recovery after CHOPS? What are the economics? How many are these crews discounted related to light crews and why are they discounted? If the growth potential is different for these crews, what are the reasons for it? What are the implications for Albert? Not all these questions will be answered in detail, but many will be addressed in various degrees of completeness. For example, a collection of all the producing and local service company that benefit from the CHOPS activity, including information about the company, is a huge task, albeit one that has merit. It cannot be achieved in this report. Rather, this report will focus on the technology of CHOPS, some of the economic issues, environmental aspects, and the possible emerging possibilities for expanding or prolonging CHOPS production in Albert as the National Energy Board of Canada's predictions of the potential for the Canadian heavy oil belt realistic, given the new technologies that are emerging. The report will address in more specific detail for the following oil areas, although different weights have been given to different areas. Definition of heavy oil are primary bitumen, a description of the crude properties of heavy oil and primary bitumen, location and size of reservoirs, review of production technologies, which technologies have been successful, which technologies are experimental, what technologies are emerging of inventions, what are the results, production profiles, what are the production economics, example of case histories, market participants, environmental considerations, research and development, estimates of future production, upgrading requirements and other downstream issues, transportation considerations, strategy considerations for oil company, the future of heavy oil in the world context, implications for Albert. What are current problems with heavy oil development? What are possible mitigative measures for environmental issues? Definitions. The major heavy oil production technology addressed will be CHOPS, cold heavy oil production with sand. CHOPS is defined as primary heavy oil production that involves the deliberate ignition of sand influx into a perforated oil well, and the continued production of the substantial quantities of sand along with the oil, perhaps for many years. For this report, heavy oil is empirically defined as all liquid and semi-solid petroleum less than 20 degree API gravity or more than 100 cp viscosity at reservoir conditions. No difference will be made between heavy oil and oil sand. Though some use below 12 API gravity and above 10,000 cp as criteria to define oil sand, and the value of 10 API gravity is often used to different between a heavy oil and super heavy oil, or bitumen, or oil sand, or tar sand, or extra heavy crudes. A definition for heavy oil could also be expressed in terms of producibility, While many assume that the oil in oil sand or super heavy crude oil or bitumen sands is essentially an immobile fluid under existing reservoir conditions. This means that the oil is so viscous that it cannot be made to flow by non-thermal oil production method or other special method, and this in turn means that there is no possibility to produce enough oil by conventional methods to profitable. While on the other hand, heavy oils have some mobility under naturally existing conditions and can flow to wells and be produced economically, with or without sand. Although the production rate in each well may be modest, such a definition is also empirical, as some low-cost operators may consider a certain production rate economical, whereas an integrated oil company would not. All empirical or foundational definitions are somewhat subjective. The writer prefers an in situ viscosity criterion to classify oils, although the specific value cannot be widely agreed upon. Heavy oil could be defined as oil having a natural flowing viscosity in the reservoir between 100 and 10,000 cp, or between 50 and 20,000 cp, or some other reasonable limits. This has the virtue of being a fixed measure and can be taken to refer to the viscosity in situation under extreme conditions. Therefore, in the laboratory, all measurements must be made on oil to which the natural solution gas and being restored, and at the correct reservoir temperature. It has the drawback of the combating two generations of industry density classification using the API scale. A common classification using the API density scale is below 10 API is super heavy crude oil, and 10 to 20 API is extra heavy crude. Dr. George Storzer, U.S. Department of Energy, retired now, advocate the following classification and in situation condition. Heavy crude is 10 to 20 API, viscosity between 100 and 10,000 cp. Extra heavy crude is below 10 API, and the viscosity between 100 and 10,000 cp. Bitumen is below 10 API, viscosity is above 10,000 cp. The world's heavy oil deposits are dominantly in high porosity, about 28%, unconsolidated sandstone. The term unconsolidated sandstone, widely used in the petroleum industry, refers to sandstone or sand that possess no true tensile strength, arising from grain to grain mineral cementation. These materials are friable, and an intact sample can be easily disaggregated with hand. As with the issues of the oil classification, there is no specific quantitative strength criteria associated with the term of UCSS, but petroleum geomechanics engineers agree that UCSS has negligible tensile strength and can be manually broken apart into individual grains. Although other older and deeper sandstone are also invariably more cemented and stronger. The definition of UCSS is a functional one and is independent of the specifics of the bureau depth, geological history, granulometry, and fabric and mineralogy. Figure 1.1 contains an approximate geographic classification of Canadian heavy oil depths. These definitions do not correspond to the Alberta Energy classification or the National Energy Board of Canada classification. EUB classifications for royalty and tax purposes are based on a geographical line, the source boundary to Township 53 north of this line, exclusive of the surface mining area in the Serbska deficit. The EUB classifies all deficits as oil sand, and the royalty regimes are determined by the classification. For a reservoir to be classified as oil sand, even north of Township 53, an application to so classify it must be made to the EUB, which will give its approval for that classification and allow the project to access a more favorable royalty regime. Primary oil production in such case is referred to as primary bitumen production north of Township 53. South of this township, such production is called primary heavy oil production. Even though the technologies may be identical, the strata contagious and the reservoir and oil properties completely similar. Production through CHOPS is therefore subject to different royalty and taxation regimes. Even though the deficit, the crude oil properties, and the extractivity methods are perhaps identical. The NEB in their studies use a classification based on physical properties. Heavy oil is greater than 12 API gravity or less than 10,000 cp viscosity. The difference between the heavy oil and the light oil is set at a density of 0.89 GCM or less than 25 API. They use the term conventional heavy oil and the functional definitions describing heavy oil that can flow naturally into a well. This definition is therefore analogous to the EUB term primary heavy oil. The definition of the heavy oil belt, it's called HOB, used in this report is largely geographical and excludes the generally more viscous above 40,000 cp cold lake deficits in the Clearwater Formation. Not all the oil in the HOB can be accessed by currently primary production technology, but the great majority, including all deposits south of Township 53 in Albert, may be assumed to be amenable to primary heavy oil production technology, assuming that the reservoir thickness and oil saturations, water zone are appropriate. 1.2 General geological setting. The target of CHOPS technology is mainly the heavy oil belts that straddle the Albert Seismic border, but there are also a number of other heavy oil deposits that may be affected by CHOPS and other new and emerging production technologies. Appendix 1 contains a general introduction and geological summary of the major aspects of the Albert deposit of heavy oil and oil sands. The major deposits are approximately outlined in Figure 1.1. The Figure 1.1 shows us the heavy and extra heavy oil sand regions. Albert, they are all high porosity, just like 30% consolidated sandstone, and with the exception of a few small heavy oil fields in Devonian sandstone in Saskatchewan. They are all found in sequence of sand and shales of critical age. In terms of total oil in place, over 95% of resource lies in Albert. 100% of oil sand deposits are in Albert. There is an area in airport called the carbonate triangle, where carbonate reservoir rocks, limestones, and dolomites, much older than the Cretaceous UCSS, also contain viscous oil deposits. It has a total oil in place volume that is on the order of 10 to 15% that in the sand. However, the carbonate triangle is fracture-dominated, highly competent, of low porosity, nearly 10 to 14%, and will require the development and application of modified or new production schemes different from those that are being used and will be developed to exploit the high porosity weak sandstone that do not have natural fractures to dominate flow behavior. Given the lower relative oil contents and the presence of the rich oil sands and heavy oil deposits, these carbonates deposits may be considered an resource for the distant future. 1.3 CHOPS and other new technologies. CHOPS, the major heavy oil production technology discussed will be CHOPS. CHOPS involved deliberate injection of sand influence into a perforated oil well and continued production of substantial quantities of sand alone with the oil, perhaps for many years. CHOPS requires management of large quantities of sand in all phases of production. This is a radically different concept to conventional oil well production management. Also, there are physical processes occurring in the reservoir that are completely foreign to conventional oil production engineers. Forming oil behavior, massive stress redistribution, liquefaction of sand, flow of four-phase slurry. Because CHOPS requires a radically different approach to oil field management, and because scientific and engineering personnel have to learn new physical principles and apply the CHOPS qualifies as a new oil production technology. It is the primary production method because it exploits natural energy sources in the reservoir, energy from dissolution and expansion of gas, and energy from the downward motion of the overburden. It is not widely understood in heavy oil exploitation that the exclusion of sand during primary production through use of screens or ground packers in vertical wells means that the oil cannot be produced economically. In individually vertical wear rates will be only a few cubic meters per day, and the best of this rate will be attained only in the lower viscosity heavy oils, it means below 1000 cp, and the better reservoirs K is above 2 and T is above 10. If sand ingress is initiated and sustained in reservoirs that have right characteristics, oil production rates as high as 15 to 50 can be achieved in almost all cases. Such rates have also been achieved without large-scale sand influx in some heavy oil reservoirs exploited with long horizontal wears. However, the cost of horizontal wear is and will remain about 3 to 5 more expensive than vertical wear, and wear intervention costs are extremely high in horizontal wears. These horizontal wears usually have a lifespan of 3 to 6 years only, and typically no more than 10% of original oil in place is produced. Data will also be presented later to show that in most cases CHOPS wells are more profitable and produce more total oil than horizontal wells. CHOPS produces large quantities of oil sands as well as various categories of fluid wastes. Chloride-rich water, water oil clay, emulsions, slopes, tank bottom sludges, and soil fluid mixed arising from spills. The handling of all these wastes, including the massive volume of produced sands, can add as such as 3 per bottle, $3 per bottle to be operates cost for CHOPS. Waste management is considered to be the major cost factor for CHOPS operations. Resulting in about 15 to 35% of OPEX, depending on oil and sand rates. Understanding and minimizing these costs are fundamental to planning and executing a heavy oil project using CHOPS methods. The other large OPEX cost category is the cost of well workovers. CHOPS will need far more frequent workovers than conventional oil wells, and this result is about 15 to 25% of OPEX, depending on the field, the wells, reducing not only the fractions of OPEX absorbed by the workovers, but also reducing all OPEX costs from the current level of about $7 per bottle could increase profits open up more marginal fields for development and also allow the redevelopment of currently inactive but not abundant wells. Before 1985 to 1990, heavy oil production was based largely on thermal stimulation to reduce viscosity and large pressure drops to induce flow. Projects used select steam stimulation, half and puff, steam flooding, wet or dry combustion using air or oxygen injection, and combinations of these methods. Until recently, these technologies employed arrows of vertical to meet widely divided wells below 45 degrees. Only 3 projects in Canada still use this old technology. Some methods have never proven viable for heavy oil. These include solvent injection, biological method, cold gas injection, polymer method, and institution emulsification up to about 1985 to 88. Marginal economic no-thermal production with vertical well was used in a limited manner in Alberta and Netherlands, but these wells produce less than 10 meters per day. Recovery was invariable less than 5 to 8% OIP, and small amounts of sand generally entered the wellbore during production. Other new production technologies. Several new production technologies have been developed and proven in Alberta since 1985. Furthermore, there are emerging technologies that may impact future heavy oil production. The technologies defined and proven are those for which several commercial projects producing oil economically have been implemented in Canada or elsewhere by the year 2001 to 2002. The discussion here is expounded in Chapter 13, Steam Assisted Gravel Drainage (SAGD), based on the current wells, involves steam injection for viscosity reduction and gravity segregations for flow. The first prototypes for were drilled from an underground mine in 1984 to 86, funded by the Alberta government, and the first commercial projects commenced producing in Canada in 2001. Cold production is non-thermal heavy oil production without sand. to achieve the economical rates. The large drainage area for long horizontal wells completed with slotted liners is exploited. In Canada, economic success in oils less viscous than 1,500 CP is common, even though their production rates may drop at 40% per year, and the OIP recovery is less than 10%. This technology has found major application in the in Venezuela, where multilateral branches and added to further increase the drainage area of each well. Pressure passing technology is a flow rate enhancement method first introduced in Canadian heavy oil fields using CHOPS in the period of 1999 to 2001. The approach applicable to any liquid saturated porous medium involves applying repeated Taylor's pressure passes to the liquid phase of the reservoir. This has the effect of suppressing achieved instabilities such as viscous fingering or permeability cleanup, overcoming compliance barriers, and reducing pore throat blockage. PPT promises to have a general value for any type of oil and has also found application as a workable method. There are also several emerging heavy oil production technologies. An emerging method is promising approach that has perhaps seen laboratory and field trials, but has not been commercial implements. The two major emerging technologies for heavy oil are VAPEX and PSI. Vapor-assisted petroleum fraction is VAPEX. From point of view of physical and flow process, the same process as SAGD, except that a mixture of considerable and non-condensable gas is used to diffuse into the heavy oil to reduce viscosity and also to cause oil swelling. VAPEX approach can be integrated in SAGD approaches in various ways, such as cycling between steam and miscible gas, using a mixture of gas in the steam, warm VAPEX using heated gas injection, and so on. As with SAGD, all VAPEX variations use gravitational stabilized flow to avoid child instabilities and achieved high recovery factors. Toe-to-heel air injection is essentially combustion, but using hardware so that the combustion products and heated hydro hydrocarbons flow almost immediately downward into the horizontal production where, rather than having to channel through long distance. These proven and emerging new technologies will, in the future, be used more and more in the hybrid and mixed modes to achieve better recovery ratios and better return on investment. For example, CHOPS gives high early production rates, but second give better recovery rates, suggesting phase or stimulations use of two methods. Also, different technologies will be found to be suitable for different reservoirs and conditions. Second and other thermal methods become very inefficient in reservoirs less than 15 zinc, whereas CHOPS and PVT have been economically successful in such cases. All these technologies will benefit from improvements in thermal efficiency, process control, and cost reductions. Appendix 2 contains a standalone summary of new heavy oil production technologies and a brief discussion of related issues. Canadian heavy oil production and upgrading. Canada is the world's largest producer of extra heavy oil. Large-scale open cast mining projects include the open pit miners in the oil sand, with upgrading facilities on site. Approximately 300,000 bottles per day of synthetic crude oil is produced from actual heavy oil. In the mining projects, EUB data for the year 2000 from these two operations are 317,000 barrels per day. In Albert can be assumed to take place with some amount of sun influx general greater than 1% by volume. A small percentage of primary heavy oil production is benefited to asphalt production. Products in the small Husky oil refinery of this. Some of it is upgraded into synthetic crude oil in the upgrader and the co-operator refinery in Regina. Both facilities designed to handle the extremely viscous feedstone. Several refineries in the Edmonton area accept heavy oil as a fraction of their feedstone, and there are programs in most of these refineries in increase of heavy oil input. Most of the primary heavy oil, perhaps 60 to 70%, is diluted and shipped to the United States for processing. The produced heavy oil has not upgraded in Canada to synthetic crude oil is shipped via pipeline to the United States after the addition of up to 15% low molecular weight HC diluent naphtha to reduce the viscosity to permit pipeline. The major upgrading and refining facility that accept Canadian heavy oil feedstocks are located in Chicago, Conventional oil in Alberta continue to slowly deplete and upgrading heavy oil in Alberta to high quality synthetic crude oil makes a great deal of economic sense because of the proximity of the hydrogen, because of a differential price that can be very large, and because of other advantages. This table shows us the Alberta crude oil and equivalent production. Increase in heavy oil vs conventional oil production. Canada's overall oil production rate, which include conventional oil, heavy oil, and extra heavy oil produced by the thermal method of or open pit mining, experienced a peak in 1983 at a rate of approximately barrels per day. Then it declined slowly for several years before again started to grow slowly, reaching a level of almost 2.1 to 2.2 barrels per day total production. In the period of September 1999 to September 2000, this oil production response, a peak followed by decline, then a reversal of the decline to achieve a level of production substantially above the initial peak. This figure shows oil production in Canada. We can see the most of this is before is conventional light and In the 1999, the conventional light oil is decreased and the conventional heavy oil is increased. Exception in the world. No other major production country has yet succeeded in reversing the deadline curve through the development of heavy oil. Venezuela is likely to be the second to achieve this in 2004 to 2005, but it will not exceed its previous peak production rate at that time. This reversal of decline behavior had not been noted during the development of any other sedimentary basin in the world. This is because there have always been new conventional oil resources that could be exceeded in other basins to meet increased demand. While searching for new conventional resources has always been more profitable and technological simpler than developing visco heavy oil. In the next decade, this may change because the exploration costs of the conventional oil are increased inexorably throughout the world. The oil production focus in Canada has shifted from the low viscosity, mediums, and light gravity conventional oil, largely in carbonate reef structure, and where consolidated sandstones and conglomerates to the production of heavy oil from high porosity unconsolidated sandstone spread across eastern Alberta and western Saskatchewan. In a mature basin, such as the Western Canadian sedimental basin, it is observed that exploration cost per barrel of new conventional oil production continue to rise until it is no longer economic to pursue general exploration unless the price of the oil is high. Therefore, if large resources that are technology challenging to develop, extensive heavy oil deposits coexist. Besides the depleting conventional oil attend, and economic investment are gradually but naturally displaced towards the more difficult research. At the same time, technology never is static. Continue improvements in technology and the emergence of novel production concepts have reduced the relative cost of developing technology challenging heavy oil resource because the marginal operating cost of technology intensive heavy oil production has become less than the exploration cost to find a new barrel of production from conventional oil, and because of the development cost and dropped recently, continued development of heavy oil. This figure shows us oil from exploration becomes more expensive than oil from technology as the basin matures. And oil sands in airport will continue unabated unless environmental factors or unforeseen events arise. Thus, in Albert, the oil industry is no longer driven by exploration but by technology developments. All basins throughout the world that have large amounts of non-conventional resources can expect a similar sequencing of events over the next few decades. The international oil industry in this other area will be in an advantageous position to profit from the technology development for heavy oil production that is being driven largely by Canadian advance. Perhaps Canadian company can be in the lead of this changing technologies thrust. Primary heavy oil production with CHOPS continued to rise in the period 1998 to 2000, despite depressed price. In the entire HOB, it is estimated that CHOPS produces about 460,000 barrels of crude oil a day, and this is 20% of Canadian oil production. It should continue to have a major impact and even grow substantially, provided that upgrading facilities increase the beneficence capacity. This is considered the major impediment to increased oil production from the HOB. Heavy oil price cyclicity. Heavy oil in Canada had a strong cyclic price history that has made it extremely difficult to maintain best business practice and has also resulted in a substantial loss of general revenues and benefits to everyone. Many professional industry personnel and economists fail to recognize that there is somewhat of a disconnect between the world oil market and heavy oil market in the West Central North America. Several important factors must be understood. Beneficiation. Heavy crude oil cannot be sent to a conventional refinery. It had too high a carbon content that there are also large amounts of sulfur and heavy metals. The massive excessive carbon content must be overcome a combination of rejection of some of the carbon and addition of hydrogen Thus, this figure shows us heavy oil has experienced several cyclic changes in price because of the production and processing capacity difference. Upgrading is needed, and this is carried out in complex and costly industrial facilities. In upgraders, large cooking towers heat the viscous feedstone to break apart the and deposit elemental carbon. The resulting solid coke with above 19% carbon content is a byproduct of limited value in Canada, as it has higher sulfur content and coke combinations resides have relatively high contents of heavy metal. After coking, uh, elemental hydrogen is formed from methane, and high pressure and temperature are used to increase the hydrogen to carbon ratio of the liquids to generate synthetic crude oil for refining. The methane for the hydrogenation process is sourced from natural gas. It is the cheapest hydrogen source for this process, and no substitute hydrogen donor source is in sight. Facility cost and cyclicity, long lead times and capital cost make investment in upgrading facilities difficult in a world oil price market that has seen large fluctuations in the last 20 years. Although heavy oil production is a vital part of Canadians' production, exceeding 45% of all oil sands mines and heavy oil production is included. The impact of Canada's heavy oil production is irrelevant in terms of the world price. Only 8% of world oil production, about 5.8 MBOD, comes from heavy oil. Demand-supply variations variations related largely to Middle East conventional oil recently result in a crude oil price drop to 10 per bottle oil. It then climbed to 33 per bottle in 2000 and dropping the late 2001 to as low as 20 per bottle. Investing in a large upgrader requires an investment exceeding it becomes impossible for both heavy oil production company and upgrading facility to be profitable. Thus, a price cyclicity is not conducive to the generation of the large capital expenditures (capex) need for upgrading facilities. The perceived risks are too high in a violent market. The price different. The upgrading facility must purchase heavy oil from producers and at a price that is sufficient to meet fixed asset capital cost or operation expense and generate a responsible profit. This price is lower than the posted price for light, sweet crude oil, and it is referred to as the differential. It is estimated that the Husky oil upgrader needs a price difference of to be reasonable profitable. It has been as low as 4.5 per barrel in 1996, and for March of 2001, it was ranged from 16 to 18 per barrel. The heavy oil price cycle. If there is a shortage of feedstock for the upgrade, the price differential becomes less, but if there is a surplus, the differential expands. In part, this is also set by the world oil price. A high world oil price allows a much higher differential in principle than a low world oil price, because there are only limited number of upgrading facilities that accept the Canadian heavy oil. When new capacity becomes available, there is a period of high demand and the differential sinks. Where producers meet these demands, the demand is low and the differential rise, with far better returns to the upgrader operations than to the production operations. As producers ramp up production after new capacity becomes available, they always overshoot, and this leads to prolonged period of excessive production capacity. This situation in late 2001. The dilemma of the small producer. In the last decade, dominantly because of CHOPS, this issue of economical production has largely been solved. The emergence of new production technologies is likely to maintain this situation. Large volume production of heavy oil is no longer a problem. It is believed that CHOPS technology could easily add several hundred thousand barrels of oil per day to the market in a period of 2 or 3 years if the upgrading facility become available. The handful of new SAGD projects initial in 2000 and 2001 will be producing at least an additional 100,000 barrels per day by the end of 2002, and this company will be to produce more efficiently and improving, and OPEX has dropped substantially in the last decade. However, small companies without guarantee access to upgrading capacity that dilemma. If they produce more, the differential rises because of oversupply. If they produce less, their cash flow can suffer. Upgrading facilities want the highest differential they can get. Producers lowest. Small producers do not colluded to fix production because companies such as IOL and Husker who have success to their own operating capacity. Simple increase production because they can obtain profits from either production or from the price differential. If the differential is high, it is more profitable to Husker oil to buy the depressed price heavy oil from other producers. If the differential is low, they benefit more from increasing their own production levels. Cyclicity example on producers. Figure 1.5 shows an example of the effect on price, cyclicity, and demand on one operator in the Albert Lamberger field over a 4-year period covering a serial cycle of price changes. The major points are as demand increased to late 1997. More and more production capacity was installed by the drilling more wells. New wells are usually better producers. With the sudden price drop in heavy oil price in late 1997, the company started withdrawing the worst well from production, focusing on the better well with lower operating costs. Well counts went from 523 to 268 wells in a relatively short period. With 1999 price recovery on the way, the trend was reversed, and the number of wells was increased gradually, mainly by rehabilitating inactive wells. However, changing difference among wells seriously affect producer profitability, requiring careful cost controls at all times. All heavy oil companies, with the possible exception of Hafr Oil, which has sufficient in-house upgrading capacity to accommodate their own production, can produce examples such as this one to demonstrate the pernicious effect of cyclicity. Note that the cost of rehabilitating a well in this study was estimated to be on the order of 25,000 and the reactivity varies, averaged in initial production rates of only 7 per day, declined to 3 per day within a year. Of course, these were the worst were in the field, not the best, which tended to produce closer to 8 average. Summary. Up to now, the relatively rapidly changing relative balance between demand and production had driven the price cycle. However, the demand for the heavy oil from the producing company is limited in the market area by the volume of the heavy crude that the refining facility companies can accept. This leads to the following cycle, which has been experienced by the heavy oil industry at least 3 times in average. Price increase, production increase. Producers lose money and are regularly bought out at bargain price by larger oil companies who may understand the value of heavy oil in the future world picture. High profits of upgrading lead to investment in alerting existing facilities, perhaps to the construction of new dedicated facility. As new upgrading is brought on stream, the price differential drops. Production is needed, and small companies once again start up in the heavy oil industry, repeating the circle. There are strong arguments to be made that this circle is pernicious, but in the absence of increase in upgrading capacity in Canada, it is difficult to see how the worst elements of the circle can be mitigated. Also, because the majority of the upgrading facilities are in the United States, large difference means direct export of potential return to the production sector, which is largely small to intermediate size Canadian company. For example, if 250,000 barrels per day heavy oil is exported and the difference is 15 bottles. And if the reasonable profit level is 8 per bottle, for upgrading at least 挣出钱 is being directly experienced the total continuing economic activity that this could generate if put toward the construction of additional upgrading facilities seems substantial. The second part, word consensual and heavy oil. Sources of hydrocarbons. What conventional oil, light oil, above 20 degree API production from Natural sources must eventually peak and enter into the decline because of the increase of world demand. In extraordinary reservoir production rate decline, a fixed, resource-based, and the indisputable fact that few new sedimentary basins remain to be exploited. Many believe this will occur in the period 2005 and 2010. Currently, consumption is about 77 MBOD. Canada produces about 2.2 MBOD. This is about 3.3% of the world total, but disproportionate amount of this figure comes from below 20-degree API heavy oil, more than of 45% of Canadian oil production, or about 1.5% of the world's total oil production. Of world production, about 7 to 8% of the total comes from heavy oil. Of the peak in world conventional oil production rate is past. Perhaps about 5 years from now, light oil production will gradually decline at a rate that will be somewhat tempered but not reversed by the gradual introduction of, among others, the new Canadian developed this figure shows us conventional oil production will peak in the next decade. Demand will be met by heavy oil, gas, other sources. Technologies such as gravity drainage and pressure passing, the advent of superior 3D seismic methods and geochemistry analysis in the last 20 years. Combined with the knowledge generated from a huge database that is now extant for hundreds of basins worldwide, mean that when a new basin is explored, the potential resource capacity of the basin can be well bounded, even if only a few exploratory wells have been drilled. Essentially, all land-based basins have been so explored, and few remote basins remain totally unevaluated. For example, the large Falkland Islands basin offshore Argentina has been explored in the last few years, and it is one of the few remaining large basins that remained untouched. Incidentally, it had turned out to be disappointing based on preliminary exploratory drilling by the Philippines and share in the period 1997 to 2000. Simply put, the world is running out of conventional oil because the world is running out of new basins to explore and exploit. Furthermore, the remaining basins are remote, and remote resources are quantity and cost limited. Exploration costs are high in deep and remote basins. Therefore, only larger funds will be developed and recovery ratios will be less than for easy basins. It is unlikely that these basins will be provide any more than another 10 to 15% of the conventional oil already known to be in place in explored basins. Nevertheless, the world will never run out of oil for several reasons. First, conventional oil comprises a small fraction of hydrocarbons in the sedimentary basin. As pressure increase in the future and as extraction methods and processing technologies are developed and perfected, such as coal conversion and shale oil extraction, these resources will become available. The time frame for this, including the method hydrate a resource in the deep ocean, is probably several generations. Second, as technology evolves, other energy sources will displace oil just as oil displaces coal. Natural gas is displacing oil in fleet vehicles in many cities, and this trend will continue. However, natural gas is a valuable resource and it too is limited. Airbus production rate of natural gas is expected to peak in the next 2 years, and for the entire world, the peak should arrive in about 15 to 18 years. The third, there are new technologies emerging for greater generator efficiency and energy recycling. For example, in 2002, the city of Los Angeles will likely start disposing of municipal biosolids through deep injection at the high temperature at depths 50 to 80 anaerobic methanogenic bacteria can degrade all the free hydrogen in the carbohydrate-rich organic waste into CH4. Within several years, and if the waste are placed into suitable geological formation, the involved gas can be collected and reused. This emerging technology is suitable not only for municipal biosolids, but can be used for any organic material. Not only will this technology generate CH4, it seems to be environmentally benign and cost competitive. with current waste treatment method, even without factoring in the value of the gas that is generated. Fourth, even if in some distant future all the organic carbon in basin is consumed, oil can be manufactured from wood or assembled from elements, giving sufficiency a commodity price. One seemingly rational replacement in ethanol production from plants carbohydrates large-scale facilities with low capital cost using genetically engineered crops that have enhanced starch contents and high production rates. It is an entirely realistic alternative to oil. Alternatively, generally optimized the methanol production can supply from plants the feedstock for fuel cells. Engines can burn H2 directly during hydrogen reforming from methane, giving a sustained high price for oil in a limited supply market. These technologies will undoubtedly be implemented in the future. Thus, it appears that in economic terms, oil is an infinite resource, not a fixed resource. Furthermore, it appears that if the commodity price for oil is forced too high by supply control, OPEC production limits, for example, several emerging technologies can be activated to address demand. This is important in the context of world price. If huge capital investment in heavy oil extraction and upgrading plants are made, if coal-to-oil facilities are constructed, and if large-scale oil exploitation operations are funded, these will not be shut down if the oil price later drops. National and corporate interests in countries that may invest in such facilities will act to keep them operating for reasons for oil supply security and other economic factors. For example, at a commodity price above 20 Canadian and Venezuela, heavy oil production and oil sand mines are economical and are being rapidly developed. Nearly 1 million barrels per day additional oil production from Canada and a similar amount from Venezuela, exclusively from below 20-degree PI resources, will gradually enter the world market in the next 7 to 8 years. If the price drops to the point where these are no longer profitable, it is unlikely that they will be closed because of the huge capital investment involved. How much heavy oil is there? World and Canadian heavy oil resource. Figure 2.2, a chart that has been widely published. The world resource is about 这些 or around 2,000 cubic kilometers of water. A cube with size 12.6 km long. There is more than twice as much resource available in below 20-degree PI oil as in conventional oil half 20-degree API. Furthermore, it is widely believed that the heavy oil resource is somewhat underestimated in comparison to the conventional oil resource because of poor quality data. Note that this amount of heavy oil does not include shale oil, a resource that is vaster but much less concentrated in terms of unit volume, and also such less accessible because of the inherent low permeability. This figure shows us the size of the world heavy oil resource. Heavy oil resources are found throughout the world, but Canada and Venezuela are similarly endowed. The two countries appear to share 35 to 40% of the world resource of the heavy oil, nearly 2.5 portals in the Canadian HOB and oil sand regions, and 1.5 portals in the Venezuelan figure. The specific amount, particularly in Venezuela, it is to a degree conjectural. It depends on the definition of what is an oil stratum in terms of thickness and oil saturation level. Nevertheless, given that similar uncertainties exist for such estimates around the world, the oil industry in many regions is only becoming to take an interest in heavy oil. The actual amounts quoted here are reasonable estimates. Other countries with appreciable heavy oil resource include Russia and China, Indonesia, as well as several of the Middle East nations were endowed with conventional, where more shallow heavy oil has been ignored because of the large production capacity of their conventional oil resource. To put the available heavy oil resource into an understand context, its size in Canada alone is so large that at a stable combined US and Canada consumption rate of 1.2 meter per year, there is enough heavy oil in Canada to meet 100% of this demand for over 100 years if the overall extraction efficiency is 13%. In the best strata, the new extraction technologies in Canada are already approaching and in some cases exceeding this recovery ratio of 30%. Oil sand miners approach 85% extraction. Imperial Oil Limited and Cold Lake is approaching 25% extraction. The four new SAGD projects initiated in Canada in 2001 expect to achieve above 50% extraction in good reservoirs. CHOPS can exceed 20% recovery. Informal pool of Canadian petroleum engineers and scientists involved in new production technologies in 2001 yielded the following estimates of ultimate recovery of Canadian heavy oil. 200% extraction with 95% certainty. 35% extraction with 50% certainty. 15% extraction with 5% certainty. Evidently, even given the persistent optimism of the engineers of the inspections for the reasonable recovery ratio are clear, a large percent of the heavy oil is currently economical and technically available, and more will become so. Using a factor of 35% and assuming that the recovery ratio from conventional oil will eventually reach 60%, there is still more heavy oil available as a future resource than all the conventional oil that has been or will be produced. Canadian heavy oil belt resources. The recent NEB report on the conventional heavy oil resource of the Western Canada sedimentary basin has identified 50 of heavy oil in place in the HOB. This is about 15% of the total resource in airport, exclusive of the air-defined carbonate triangle. They estimated that 21% of this can be recovered from currently technology. This is 1,000 days of supply for the entire world at currently consumption rates, given Canada's large population. It is of huge economic importance with a current commodity value somewhat below 3 at the world price of US 25. Given the technological progress that is ongoing, referring to the 50% probability estimated of Canadian industry engineer, the NEB estimated of the technological accessible reserved in the HOB is conservative, perhaps by a factor of 2. The writer believes that a reasonable estimate of recovery from the HOB in Canada is on the order of 150. Importantly, based on the interaction with many producers, the NEB published estimated of the amount of economical producible oil. If operators can accept the total cost of 13 per barrel, 80% of the HOB resources is economically accessible. This can be compared with the average price of what 18 to 25 that producers received in the period from January to September 2001. Apparently, primary heavy oil production through CHOPS method is currently quite profitable, despite the historically highly different price between conventional feedstock and heavy oil. World issues. The apparent richness of the world resource based present here is a radically different picture from the narrow view of resource limits approached several decades ago with great publicity in the Western press. In fact, those who claim that the world is greedily and determinedly consuming irreplaceable resource and short-changing future generations consistently ignore technical progress, market price, and the historical record. Commodities have never been cheaper. Efficiency and productivity are increased, and new ideas such as deep solid injection may generate new sources of energy, even energy recycling. It is interesting to read the prediction of doomsayers in the context of continued technological advance. For example, the Club of Rome in 1972, using exponential growth assumptions and special extrapolations under static technology, ignoring new ideas and even ignoring basic economic principles, predicted serious commodity shortage before the year 2000, including massive oil shortage and famine. The world has not seen these events. There is a smaller percentage of the world populations that suffers food than in the past. Metal recycling and replacement has reduced the need of the new mine as countries develop greater efficiencies and better technologies have resulted in the environmental improvements. The world population is no longer predicted to exceed 10 billion. Also, oil supplies continue to be generated and will so continue. Mm, This is not to say that there will not be fluctuations in prices as supply and demand disparities arise and as a particular problem evolve. Large capital investments and lead times are required for massive increase in heavy oil production. For example, in Canada, an investment of about 12 billion will be made in the period 1998 and to 2006 to achieve an additional 800,000 to 900,000 bottles per day production. The four large projects will require similar aggregate capex to achieve a similar production rate, about 750,000 bottles per day by the year 2005, having started as early as 1998. The scale of such investments suggests that if the oil price rises again in the future for a prolonged period, retarded development should later lead to supply shortfalls and price increase, a cycle not unlike the Canadian heavy oil price cycle discussed in the section. Price fluctuations may also arise because of the political instability. The large Middle East oil reserves are found in countries that have only vast-scale democratic institutions and economies based almost exclusively on oil exports. These countries, along with several other OPEC countries that are politically unstable, such as Nigeria and Venezuela, will be providing over 15% of world supply by the year 2010. There are substantial risks for oil supply interruption for the major importers, Europe, Japan, and United States. For example, the Gulf War of 1991 caused a sharp spike in price, even though there were few interruptions in supply as the Persian Gulf states agreed to ramp up production to meet losses of Iran and Kuwait. It appears that a concerted effort by the Western democracies to encourage a peaceful shift to democracy and the integration into the world trade system can only be of long-term benefit to all the importing and exporting countries alike. A policy of propping up non-democratic regime for short-term oil supply integrity is not likely to be beneficial over a period of decades. What does all this have to do with heavy oil and CHOPS technology? First, the new production technology proves that science and knowledge continue to advance. We can look forward to further advance. Second, oil prices were not and remain high indefinitely. There are alternative technologies such as synthetic oil from coal waiting in the wings. Third, the new technologies have been forced the circumstances to become quite efficient and profitably, even with unfavorable refining penalties. Fourth, exploration costs for new conventional oil production capacity will continue to rise unceasingly in all mature basins, whereas technologies such as CHOPS actually can lower the cost of technology-based oil. Fifth, there is technological feedback from the heavy oil production technologies that is improving conventional oil recovery ratios. Sixth, the amount of resources and heavy oil is UCSS is vast, and this may come to dominate the resource picture in the next generation. Thus, though it is obviously that there is a limit of the amount of conventional light oil in the sedimentary basin, and this is relevant to the oil industry in the short term. It is likely to be inconsequential to the energy industry in the long term. It appears that the world is entering a phase of large-scale development of heavy oil. Canada, by virtue of its vast resource and by virtue of consistent investment in new production technologies over the last 40 years, appears to be unequivocally favorable position to benefit from this development. One factor may seriously affect the development of heavy oil. Concerns over permanent atmospheric volume from CO2 generations have given rise to an increasing strident demand for massive reductions in oil consumption, imposition of the carbon tax and other solutions, even given the uncertainties involved in this concern. Based on the history of the world, technological developments are as likely to solve this potential problem as is the burden of the HC economic. Biosolid injection resource is about 40% of the dry mass of the organic matter remaining in place as elemental carbon permanently, sequentially, and this is the cumulative effect. Other technologies involving sequestration of CO2 are being investigated. Nevertheless, the heavy oil resources are carbon-rich, and there will be increased pressure in the next 30 years to address this issue. One possible particular solution is to increase the coking percentage in heavy oil processing and to dispose of the coke through deep well injection. There are other possibilities. For example, H2 from CH4 is currently also used in increase the HC ratio, but other sources of cheap H2 may evolve. This may eventually displace liquid HC consumption in the vehicles. Arguments can be made that, environmental issues aside, Canadian heavy oil resources should be developed only slowly, preserving the resource from generations far into the future. For example, if Canada stopped exports and only met its own needs from the heavy oil base using currently consumption values, there is no doubt that there is enough oil for 1,000 years. This argument is deeply flawed, given the known resource base. Within a century, new technologies with implements that will displace oil as a primary energy source. The history of the new technology development is clear. As a new technology is perfected, it inevitably drives out the old technology. Co-development in 1750 to 1900 drew out wood as the primary energy source. Oil displaced coal in the last century. Natural gas exploration is substantially reducing the need for the new oil production. The new energy system of the future, whatever it's based on, will drive out oil and natural gas as the primary energy sources. If we attempt to guard the heavy oil resources by production limits sometime in the future, like about 100 years from now, the resource will be abundant in favor of new energy system, and Canada will follow the rest of the world in the gradual conversion. Should the oil be preserved as a petrochemical feedstock for plastic and other products, the amount of oils so consumed is a small percentage of world consumption, and various replacement will rise with time. Preservation arguments for feedstock supplies are also flawed. It appears that if Canada does not aggressively develop its heavy oil resource base, it will be left in the ground. Nevertheless, there are forces demanding this action, based largely on concerns over global warming. These issues have to be studied and addressed.